Hello everyone, welcome back to our channel. Today we are diving into an essential graph traversal algorithm known as breadth first search, shortly BFS. This algorithm is the backbone of many real-world applications from social networks and web traveling to Google Maps and even video games like Pac-Man. In this video, we will walk you through what BFS is and how it works, a dry-run example to make it crystal clear, its time and space complexity, a Python implementation demo, and some cool applications including how it helps solve mazes. Plus, we will show how BFS shows up in popular media like Finding Nemo. This is a complete guide brought to you by Abhishek, Sudil, Saumya, Sulav, Utsav, and it's perfect whether you are a student and just brushing up on algorithms. So stick around till the end for a fun question and answer session, and don't forget to like, share, and subscribe for more tech breakdowns. Let's queue up and start exploring BFS style.
Hello everyone, my name is Sulav and I'm going to explain about the graph. So basically a graph is a collection of nodes and edges where nodes represents individual entities and edges represents the relationship between them. So from this picture you can see that A, B, C, D and E are the nodes. So a graph can be directed or unidirected. Or directed graph means it have a certain direction and unidirected means it doesn't have any direction. A graph can be either weighted or unweighted. Weighted means it have cost and unweighted means it doesn't have any cost. So talking about the BFS or the breadth first search algorithm, it is a search algorithm that traverses a graph level by level. It uses a queue with first in first out approach. It means the first element to be inserted is the first one to be removed. So it visits all the neighbors before going deeper. It means that it traverses or it searches horizontally. Like if there is A in the first row and BC in the second row, it goes from A, B and C from left to right and horizontally. So talking about BFS algorithm steps, we start at the source node or the root node, and after that we add to queue and we mark it as visited. And after that, while the queue is not empty, we dequeue that node from the queue. We visit its unvisited neighbors and we enqueue them. So we can see this in further example in another slide. So talking about an example, you can see this graph where A is the root node while applying BFS traversal on this graph. So firstly, there is A and the child nodes of A are B and C. So we move from left to right horizontally or level by level. So the traversal is A, B, C, D and E. So now I'm going to explain about the implementation of an algorithm using queue. So basically while implementing we can think it like we will insert the node or an element from the rear end and we will remove it from the front end. So from this table or a chart we can see that A is our root node which is inserted into the queue, and after that B and C are the child nodes which are inserted while using BFS traversal like horizontally or by level from left to right. So after that we have removed B from the list or queue and inserted it child node D at the end of the queue, and the queue becomes C and D, and we mark A and B as visited and the output will be A and B. After that we remove C from the list or the queue and insert its child node which is E at the rear end, and the queue becomes D and E. So after that we mark A, B and C as visited and the output will be A, B and C. So after that we will remove D from the list or the queue and try to insert its child node which doesn't exist. So there will only be E in the queue, and we mark A, B, C and D as visited and the output will be A, B, C and D. After that we will remove E from the list or the queue and mark A, B, C, D and E as visited, and the output will be A, B, C, D and E. So this is the basic implementation of an algorithm using queue.
Now I'm going to explain about time and space complexity of breadth first search. Now, let's talk about the efficiency of breadth first search. The time complexity of BFS is omega notation B plus E, where B is the number of vertices and E is the number of edges. That's because BFS visits every vertex and inspects every edge exactly once in the worst case. The space complexity is omega B. This is due to the additional memory used by the queue and the visited list, which can grow up to the size of the vertex set. So overall, BFS is highly efficient, especially for sparse graphs. Now, let's move to Python implementation. Here is a look at BFS in Python. We have used a dictionary to represent the graph, a deque for the queue to ensure efficient first in first out operations, a set to keep track of visited nodes. The logic is simple. We start with a source node, enqueue it, mark it as visited, and then while the queue is not empty, deque the front node. Visit all its unvisited neighbors, enqueue them, and mark them as visited. This implementation ensures BFS runs smoothly and avoids cycles. Now we dive into the differences between BFS and DFS. Let's compare BFS and DFS. BFS uses a queue while DFS uses a stack or recursion. BFS explores level by level, ensuring the shortest path in unweighted graphs. DFS dives deep first, which can be more memory efficient in some cases. BFS is better for programs like shortest path or spreading process, whereas DFS is suited for problems like topological sorting or cycle detection. Choosing between them depends on the problem of the context. Now we will move to the applications of BFS. BFS has real-world applications like in many fields. In social networks, it helps find friends within a certain distance or level. In Google Maps, it finds the shortest path if all roads are unweighted. In web crawling, it indexes pages layer by layer. In network broadcasting, it ensures messages are delivered to all connected nodes. In short, BFS is perfect when we want to explore all nearby nodes first. One example is maze solving. BFS is also useful in solving mazes. It explores all directions equally and guarantees the shortest escape route when paths are unweighted. This makes it ideal for building maze solvers and game AI logic. BFS is also famous in pop culture. You may not realize it, but BFS even shows up in pop culture. In Finding Nemo, the search across the ocean mirrors a BFS style level-wise search. In Pac-Man, the ghosts often use BFS to find the shortest path to the player through the maze. This fun example shows how BFS powers even the logic behind games and stories. And lastly but not least, the question and answer session is here. Let's answer a few quick questions about BFS. What's next in the queue? The next node to explore following first in first out order. Does BFS find the shortest path? The answer is yes, but only in unweighted graphs. How does BFS handle cycles? The answer is using a visited list or set to avoid revisiting nodes. Can BFS work in disconnected graphs? The answer is yes. We just run BFS on each disconnected component separately. And to wrap things up, let's quickly recap what we have learned about breadth first search BFS. BFS is a graph traversal algorithm that explores nodes level by level. It uses a queue to manage the traversal order and a visited list to avoid cycles. It's ideal for finding shortest paths in unweighted graphs. We have seen its time and complexity of Python implementation and how it compares to depth first search DFS. And we explored its real world impact from maps and social networks to maze solving and even pop culture. BFS may seem simple, but it's incredibly powerful and widely used in the real world. If you found this video helpful, make sure to leave a like, drop your thoughts or questions in the comments, and subscribe for more algorithm breakdowns and tech content. Huge shout out to our project team, me, myself, Abhishek, Sulav, Sudil, Saumya, Utsav. We have worked hard to bring you this project in a fun and informative way. Thanks for watching, and remember, in the graph of life, always keep exploring one level at a time. See you in the next video. Thank you.